Okay, we have already talked about a lot of things in Chapter 8. And today we're going to talk about some more bits and pieces that may or may not seem like they go together. And then tomorrow we're going to add 2, and Wednesday we're going to put it all together. So at this point, things you should know about. You should still know about everything from Chapter 7. So you should still know how to talk about an association, direction, form, strength, outliers. You should still know a lot of things about correlation, because correlation is still relevant. Right? Correlation gives you a measure of strength. It also gives you the direction. You should know about residuals. You should be able to calculate a residual. Shouldn't be a problem. You should be able to write an equation of the linear model if you're given the standard deviations and the means. And so you should be able to write a model based on those formulas that I gave you. They're on the formula sheet if you need to use them. You should be able to talk about slope in context. Talk about y-intercept in context. You should you should be able to say if it's appropriate, because you can look at a scatter plot and say there's 2 quantitative variables. It's a linear relationship and there's no outliers. That's already a lot of stuff. And I'm going to add more stuff. All right? This is a very meaty section. It's only 3 chapters, but there's a lot of stuff. All right? And then you're going to be like, okay, well, I got it. And then you're going to forget all of it. And then it comes back to haunt you in the very last chapter of the book. So I'm just letting you know how that's going to work. So today, first thing we're going to talk about is residuals. You guys already know how to calculate a residual. Like, that's nothing new. You did it last week. You did it on the homework. Not an issue. Residual is generally represented by the letter E because it stands for error, not in a bad way. In statistics, we have lots of errors, but they aren't like bad errors. It's as in there is variation from model to model. There's variation from survey to survey, from experiment to experiment. And so that's just the error in the predicted value and the actual value. So that's not a bad thing. Okay? So actual minus predicted, that's no big deal. We could find an individual one. We want to know how well the model fits. We can ask instead what the model missed. And so what we're going to do today is talk about residuals plots. Okay? Any questions about how to calculate a residual? All right. So residuals help you to see whether the model makes sense. If a regression model is appropriate, a linear model, all right, think about this with me, then you have theoretically drawn a line through the middle of your scatter plot, right, through the middle of your points. And so there's some points above the line and some points below the line. Some of you are like really close, some of you a little farther away, right, because it's supposed to go right through the middle, right? So if we look at the residuals then, the scatter plot of the residuals, there'll be some that are positive and some that are negative, and they should be like equally scattered about, right? So there shouldn't be anything happening in a residuals plot, okay? So in a scatter plot, you're looking for a linear relationship. Once you start looking at the residuals, though, you shouldn't see anything going on. It should be random. It should look random because, again, there should be some above and below the linear model. It should be equally scattered about, so it shouldn't have any pattern to it. All right? So a residuals plot should be super boring. This is an example of a residuals plot. You have the x-axis, which is in this case the Burger King protein situation, and the residuals. And you can see that there's no form, really. There's no direction, right? It's super weak. That's what you would want to see. All right? The residuals plot is going to answer the question, is the model appropriate? Okay? That means look at a residuals plot. Now, sometimes they're going to give them to you. Like on multiple choice questions on the AP exam, they're going to say, here's a scatter plot, here's a residuals plot, and then they're going to ask you some questions. For a free response, they'll give you a scatter plot, and they'll generally give you a residuals plot. On the ones we've done so far, we don't have the data, so we can't find all the residuals, but they might give you a residuals plot to look at. Okay? Tomorrow in class, we're going to talk about what happens when you have a data set, because we can find the linear model really quickly in our calculators. So then we can find a residuals plot in your calculator. So we're going to go ahead and do that today. We're going to look at the residuals plot in your calculator so you know how to calculate it and look at it and know where it's coming from. Okay? So everyone needs to get their graphing calculator out. And if you would put these numbers in your two lists, this is that fat and calories example I keep using from like chapter 7. I just haven't deleted the numbers out of my calculator yet. I'm going to pass out the directions and then I'll walk you through it. If you'll type in those numbers first. All right, let me know when you guys have all of those numbers filled in. Does everyone have those typed in? Almost. Super close. Okay. In order then to find the residuals, because we're going to need to find the residuals first so we can make a residuals plot. Lucky for you, your calculator does most of that for you. All right. Here's what you need to do. Your calculator will do the residuals automatically based off of the last regression analysis you computed in your calculator. So let's say you had some other stuff on your list and you happen to have run a regression analysis, which is where you would find R, so we've done that before. And then you went and typed these numbers in and skipped the part where you find R and just found the residuals. It's going to find the residuals for the old stuff. All right? So the first step is always to run a regression analysis so that you make sure the calculator knows what data you're using. Okay? So you'll go to Stat Calc number 8, like we did last week. Calculate. You'll get R like we talked about before. But none of this is relevant to me right now. We're just making sure that it did the regression analysis in the background. Okay? And it did. Excellent. All right? So we can clear that out. We don't need that. Okay? We want then, so right now in the calculator's memory is stored that equation for the linear model. We'll talk about where to get that tomorrow in class, but it's stored in the model in the calculator. So we can go through and put all of your x values into the equation and figure out the residual for all of them. And it'll fill it in for you automatically. So here's what you got to do. Go to Stat, Edit. Go to Stat, Edit. Scroll up to where your cursor is on L1. And then scroll over past all your blank lists, and generally after list 6, you'll get to a blank cell. If you have a TI Inspire, I think you can just type it in as the title because you have blank cells on every one. I know, but your spreadsheets are like this. I mean, they're just lists. So I think you can just type them and about ready to type in. Does everyone past list 6 have a blank space? Like on my screen, like there's list 6 and then there's nothing else. Great. Keep going. I know. Does it finally get to one that's blank? Does it finally get to one that's blank? It has an A. I mean, that's just alpha lock. So does everyone have their cursor on a blank title? Yes? Okay. So what you're going to do is you're going to type in, it understands that calculator function, resid, as in residuals. So you're going to type in R-E-S-I-D. The A in the corner just means it's on alpha lock, so you can already type it in. Like you don't have to change it to alpha. It's already there. So R is above the time symbol, E-S-I-D, and then hit enter. And it should automatically fill all the residuals in for you. I'm pretty sure on the Inspire you can just type that in as the title. If not, let me know. Just hit enter and it should fill them in for you automatically. Did everyone get residuals filled in for them once they hit enter? We'll work on the Inspire in a second. And it should fill some numbers in. Did you do stat calc 8 a second ago? I know, because you're using one of my calculators and everyone did it first period. All right, now that you have it there, it should stay there. Like it won't delete itself. So it's really important that each time you put new lists in, list 1 and list 2, it won't automatically change it until you do a regression analysis, okay? So if you change the numbers to new data, go do stat calc 8, and then it'll fill the right numbers in. If not, they'll stay the same until you do that. I'll figure out the Inspire in a moment. Okay, everyone with me? Then we're going to make a residuals plot. We're going to make a scatter plot. So second, stat plot. List 1 will be your X list, and then Y list, you just type in RESID again. Graph, and make sure you hit zoom 9. And that's the residuals plot for the data that we put in the calculator. And you can see there's nothing exciting going on. There's no pattern. There's no strength to it. Anything. Questions? So everyone knows how to do that now. If you're looking at a picture, you know that you're looking for nothing. Right? Okay. So this is why that's important. Last week I said that you had 3 things you had to check for when you were going to say if something was appropriate, right? Is the model appropriate? Well, you still have those 3 things. You need to look at the scatter plot and make sure there's 2 quantitative variables. You need to make sure that there's a linear relationship. And you need to make sure there's no outliers. But that's just the first step. Then you need to make a residuals plot and check that there are no obvious patterns. You don't want to see any bins. You don't want to see like the residuals all packed together on one specific spot. You want to see them spread out. You don't want to see any outliers. Okay? So again, if it says, is the model appropriate? Is the model appropriate? You would check all of these things if you have the ability. Okay, so you don't just check the scatter plot if you have a residuals plot available to you. You don't just check the scatter plot if you have all the data, because you can do the residuals plot. All right, so you should mention both of those things, scatter plot and residuals plot. Question. You want to check this before you go through all the work of doing the model. Because if it's not appropriate, then you don't want to do the model. A residuals plot might have a bend in it, so there might be a pattern, like it might look like this. If for some reason your data at just quick sight looks linear, but when you fit the line to it, it's really not. There's actually a curve in the line, or in the scatter plot. There might be then a curve in the residuals plot. All right, and that would be like, oh, the original data is not linear to begin with, so I shouldn't do this. Okay, so it's just helping you confirm that yes, you have a model that's appropriate, or no, you do not. Questions about residuals? All right, then we're going to move on. You could answer this question. It's not a problem. All right. The residual standard deviation. This is kind of confusing. You won't be asked about it very often, but we're still going to use the same things we've talked about with standard deviation multiple times. If the residuals show no interesting pattern when we plot them against x, we can look at how big they are. Because we're trying to make them as small as possible because we want them to be close to the line, right, the linear model. Since their mean is always 0, it's only sensible to look at how much they vary, right? That's what standard deviation does. It tells you how much something varies. The standard deviation of the residuals is represented by S with an E subscript, because that's residuals. And it gives us a measure of how much the points spread around the regression line. So it's just going to give you how scattered everything is. How scattered. If you have the residuals, you can make a histogram of the residual. If it's close to being unimodal and symmetric-ish, then you can use that 68, 95, 99.7 idea. All right? So if you're within 2 standard deviations in the residuals, then nothing unusual is happening with the original data point. Right? And we'll see that in play in a second with context. All right? So we know that 95% of the residuals should be no larger in size than 2 whatever the standard deviation is. So if you have residuals that were very large, then maybe that point is extraordinary to begin with. Maybe it was an outlier to begin with. So this is just speaking to the residuals. Does that make sense? But we still use the same ideas with standard deviation. It's going to come up in a question in a second, and I think it'll make more sense. All right. This is residuals plots is number 1 big topic today. Second big topic is R-squared. Okay? R-squared is very important to your life right now. First of all, what does R stand for? Correlation. R-squared is legitimately the correlation squared. Don't get that twisted. All right? So if you know the correlation, you can find R-squared because you just square it. If you know R-squared, you can find this correlation because you can just take the square root. All right? They are directly related in that way. Now, if you were going to take the square root of R-squared to find the correlation, then what would you need to decide? If it's positive or negative. So you would need the scatter plot or the linear model or something to determine if the slope or the relationship is positive or negative. All right? So just be careful with that. Make sure you remember that you have to look at a sign as well. All right. Here's how I'm going to explain this and see if you can follow. If your linear model had a correlation of 1, right, that means that we have a perfect positive relationship, right? Every single point is on the line. Does that make sense? What would all the residuals values then be? 0, because the actual and the predicted would be identical, right? So they would all be 0. Okay? If all the residuals were 0 then there would be no variation around the line, right? Everything will be on the line. Okay? And R-squared talks about the variation accounted for by the model. If there is no variation, because everything's on the line, then 100% of the variation is accounted for by the model, right? Because R is 1, 1 squared is 1. You repeat R-squared, you talk about R-squared in percentage form. So 100% of the variation is accounted for. Everything is on the line. There is like none left. Does that make sense? Yes or no? Okay. But we know in real life that nothing is going to have a correlation of 1. Like, it's just not going to happen, right? It's just not perfect like that. So R-squared is telling you what percent of the variation is accounted for by the model. And then you have an alternate percentage we don't talk about very often, but it gives you the percent of the variation that's accounted for by other things maybe lurking in the background that we don't really care about. Okay? So R-squared is going to give you a percentage of the variation that's accounted for between the variables. R-squared is another one of those things. So I'm going to give you a template when I pull this shade down in a second. And if you don't write it that way, you will get the answer wrong. They're going to ask you about R-squared all the time. Anytime you're doing a scatter plot, they're going to ask you about the slope in context, the y-intercept in context. They're going to ask you to interpret R-squared. And there is no flourishing and making stuff up that's better than the sentence I'm giving you, because you'll get it wrong. We say that R-squared percent of the variation in whatever your y variable is accounted for by the x variable. And this should help you with how well the model fits. That's not the template, but that's just going to help you with how well the model fits. So back to our example with the correlation of 1 and R squared is 100%, right? Then if I asked how well the model fits, well, 100% is the best it can be, right? R is the best, R equals 1 is the best it can be. It fits amazingly well, right? So the closer you are to 100%, the better your model fits. So if your R squared is 80%, then your model fits your data pretty well. If your R squared is 20%, it doesn't fit so well. But it's the best we can do, right? We already talked about you can only have one linear model. It's the least squares regression line, right? So there can't be any other ones. It just doesn't fit very often. Maybe that just means that your data is way spread apart and it's just not good to begin with. So here's an example from the book without having to write anything out about R squared. Our regression model that predicts maximum wind speed in hurricanes based on the storm's central pressure has R squared of 77.3%. So here's how they interpret that. 77.3% of the variation in maximum wind speed can be accounted for by the hurricane central pressure. So if they're asking about R squared, that's what you would say. But that means that there's still a percent left over, right? You do it 100% minus 77.3%. There's still a certain percentage that's left over that has to be accounted for by something else. So here they say other factors such as temperature and whether the storm is over water or land may explain some of the remaining variation. You're never going to have to go into that much detail and explain where the other variation came from or comes from. But you have to realize that there's other variations still not being accounted for. That's where we talk about lurking variables and stuff. That goes back into why we can't say that something causes something else. All right? So it's all of the stuff we've been talking about is related. Okay? R squared is an important measure because, again, it tells you how well your model fits, and it talks about how much of the variation, which we're talking about, like how scattered it is about the line, how much of that is really accounted for between your two variables, the ones you're looking at. Does that make sense what the R squared measures? Okay. So here's some questions we should be able to answer. Back to a regression of house price in thousands of dollars on house size in thousands of square feet, the R squared value is reported as 59.5%. And the standard deviation of the residuals is 53.79. So we'll be able to use that in a second. I think it'll make more sense. What does the R squared value mean about the relationship of price and size? That means interpret it. That means let's talk about that through that sentence we just wrote. So that means that 59.5% of the variation in house price, because price was our Y variable, is accounted for by house size. That's what that means. You have to know that sentence. So know that sentence. Is the correlation of price and size positive or negative, and how do you know? So first of all, how would you find the correlation? Square root of R back in decimal form. So square root of 0.595. All right. So how do we know if it's positive or negative? What would I need to look at? Yeah, I need to look at the scatter plot or the model so I can see either the direction of the scatter plot or the slope, the side of the slope in the model. So the model was right here. So is the slope positive or negative? Positive. So that means that R is going to be positive. Does that make sense? Okay. If we measure house size in square meters instead, so we're changing from square feet to square meters, we're changing units, would R squared change? No, why not? Because R and R squared are based off the same thing, right? Correlation doesn't change if units change, so R squared doesn't change if units change. Yeah? Would the slope of the line change? Yes. So far, we talked about calculating slope using R times the standard deviation of Y or the standard deviation of X, right? Well, if you change the unit, that changes the standard deviation, right? So you're going to change the slope. Okay, so you change units, you're going to change the actual slope, but it does not change the correlation. Question on that? So that would be no, and that would be yes. Okay, 14. You find that your house in Saratoga is worth $100,000 more than the regression model predicts. That is a residual. That's what it's telling you. Right? It's $100,000 different than what is predicted. So that's a residual. Should you be very surprised as well as pleased? So now I have the standard deviation of the residuals, right? I'm talking about a residual. So if everything was unimodal and symmetric, if it was, then about how many standard deviations above or below the mean would we say are extraordinary? 2 or 3, right? Doesn't matter which you go with, because both of them are standard, that's normal. I'm going to go with 2, whichever. So if I do 2 times the standard deviation of the residuals, 53.79, I get 107.58. This is in thousands of dollars for price, remember that? So times 1,000. Then 2 standard deviations above the mean in the residuals would be $107,580. So should I be surprised that my house is worth $100,000 more? Not really, right? That's less than 2 standard deviations above the mean, right? So it's not extraordinary. So we're still using the standard deviations in the same context that we used them before. We're just using it for the residuals. Does that make sense? Okay. Question so far? All right, so we're going to get ready to talk about what could go wrong in this chapter, but the 2 big things you have to talk about today. We have a residuals plot, so we know all the things we're supposed to check before we even do a model, all right? And then we've talked about R-squared. They're going to talk about R-squared over and over, and they're always going to ask you about it, okay? Talking about variation, it tells you how well the model fits, all right? The higher that percentage is, the better it fits. So those are important things to note for today. Now here's the things that can go wrong. We've talked about a lot of these in depth in chapter 7 and now, but we'll go over them again. Don't fit a straight line to a non-linear relationship. We know better. Don't try. You only know how to do linear models, so don't try to be fancy and make a linear model for something that's not linear. Beware of extraordinary points as an outlier, so be careful of those. We know that they can have an effect on the correlation. They can have effect on the model that you create, so be careful with that. We're going to go back to this one. Don't infer that X causes Y just because there's a good linear model. Just because the model is great does not mean we have causation still. Don't try. There's never proving things in statistics. Sorry for you. Don't choose a model based on R-squared alone. So R-squared tells you how well something fits. Let's say R-squared is 80%. That means it fits really well. You can't not look at the scatter plot and the residuals plot and all that stuff too, though. Okay, just because R-squared is high does not give you the right to just be like, yeah, okay, it works, it's fine. Not happening. Okay. And so the last one we haven't really talked about, but it says don't extrapolate beyond the data. So if you have a scatter plot, and let's say we're talking about fat and calories and burgers because we keep talking about that, okay? If you have fat grams, your x-axis, that range from 20 grams to 40 grams, all right? And then you make a linear model to find calories, wonderful, we could do that, not an issue, right? But then it asks you to predict how many calories a sandwich would have if it had 70 grams of fat. I don't know what happens beyond 40 grams, right? I can only check all those conditions we've been talking about up to 40 grams, right? I only know there's a linear relationship up to 40 grams. I only know that there's no outliers up to 40 grams. I only know that the residuals plot is boring up to 40 grams, right? Outside of that, it's nice to have a model to try to make predictions, but if we start going outside 40 grams, anything could happen. We don't have any data for that. Like we could have curve stuff going on. It could have like crazy outliers or be all over the place, which would make our model a little bit different. We don't have any data, so we don't want to extrapolate. That means picking out or making predictions off data that we don't have any knowledge about, okay? So I know it's tempting, but we really can't do that in this class. Does that make sense? Yeah. Okay. here's the assignment. It's going to be due Wednesday. Tomorrow.